All right, welcome to physics. Today we are moving on with our motion learning target, and we're going to be looking at acceleration now. Just a reminder, we were just looking at constant velocity, and so scenarios where an object is moving at the same speed the entire time, or at least the average speed. So both kind of work in that scenario, and so we use the linear equation, and we also refer to it as a linear pattern because the distance and the time when you plotted them on a graph would make a straight line with that constant velocity. Well, now we're looking at this concept of acceleration, and I would guess that most of you are familiar with acceleration in the sense that, well, that's when something speeds up, but uh, it's also slowing down. And so both can be referred to as acceleration, but we often differentiate with acceleration as deceleration for slowing down and acceleration for speeding up. But technically, both are forms of acceleration. You might have a negative acceleration or a positive acceleration. So that's something to keep in mind as we are looking at acceleration and this new scenario, new types of scenarios. And uh, let's go through the slideshow to further this. So one of the reasons why we're going through this, okay, is again, we're here in our learning target. You want to be looking and being able to make a prediction graphically, mathematically, in data tables as well. And we just did that for linear, and you'll see that the next one is quadratic. So now we're moving on to this quadratic, and we're going to be looking to identify, compare, and contrast the patterns with this concept of rate of change, which is when we were looking at our linear model, and now we're going to be introducing the quadratic model and how that represents motion. So again, straight from the learning target, this is what we're covering. It's a lot, but you're doing fantastic, so keep up the good work. Comparing the two, so I want, because that's specifically in learning target, I wanted to compare the two. Well, we looked at, okay, distance versus time. That's the kind of data we were collecting, and we were looking at constant velocity. And so what did that look like? And it really followed a linear pattern, and so we were able to use the linear equation to solve for it. And then we had distance, velocity, time, and starting distance to kind of plot that or make predictions, right? And we practice that a lot. Now we're using what's called the quadratic equation. And so that's y equals ax squared. And so y is going to represent distance. A is going to be your rate of change. Also, we'll refer to it as acceleration. Okay, how quickly is it accelerating or changing that rate? And x then will be your time. When looking at the motion graphs, uh, depending on what you're plotting and depending on what the scenario is, it's going to look different. But we see here, these are three examples of linear patterns. Okay, so the slope is zero, which means the velocity in this scenario is zero. And if the velocity is zero, then that means the object is not moving, it's sitting still. Now, this one, okay, with distance versus time, constant velocity increasing, or, uh, you know, sorry, I apologize. Constant velocity, whatever the rate is, will be moving in a straight pattern. You'll go this far for every second. And so you'll see that it's an equal and that linear pattern. This, we didn't talk too many scenarios with this negative velocity, but this would be slowing down at a constant velocity. Or no, I apologize. It'll be getting closer. it'll be getting closer based on the position versus the time. So this would be really traveling away. This would be traveling towards us, and so those are how those are related. Uh, and then now we're looking at quadratic, and so hopefully you see right away the difference. We have this curved line. Velocity is not constant, but the velocity changes. So early, it's going slower. As you are increasing your velocity, you're covering more distance in a shorter amount of time, and eventually you're going faster. And so you've accelerated in that scenario. Again, looking at acceleration more, we have accelerating and decelerating on these graphs, and you can see the difference. This one maybe starts out fast and then begins to slow down over time. This one starts off slow and begins to speed up over time. So those are acceleration and deceleration. But again, it can also be referred to as negative acceleration. Now, just like with our linear pattern, we were able to solve for distance, we were able to solve for time, we were able to solve for velocity, and now we're going to be uh, still able to solve in really two different ways. So we have solving for distance. Um, yes, so solving for distance, and so distance equals acceleration times time squared. Solving for the rate of change would be a equals, okay, that's going to be your acceleration equals distance divided by time squared. And solving for time is time equals the square root of distance divided by acceleration. So again, similar to what we've just done, we're going to practice this with acceleration and these different scenarios, but we can look at, again, the different variables, and that really is presenting more information or wording the question differently. And then we also have this one here, another way of solving for acceleration where we can use velocity. If we know the initial velocity, okay, that's going to be VI, and we know the final velocity, right? So how fast was it going when it started? How fast was it going when it ended? And how long did it take? So time. We can also solve for then what was the constant acceleration there. Now the units are something that are going to be slightly different. You'll see that we have a change of velocity per second. So this will be meters per second, or you can also say that as meters per second squared. Then we have kilometers per hour per second. So again, if you're in a car, this would be really in another country. So let's look at this one, miles per hour per second. So if you're a car here, okay, you're going miles per hour. That's how we look at the speed of a car. Well, so we can calculate the rate in which your velocity, in which your speed is changing every second. And so that'd be like you're sitting at a red light, you then accelerate, and you know, how fast did your rate change? How fast did your velocity change uh, every second that you accelerated? All right. Next, I want you to watch this video about acceleration. What is acceleration? It has great visuals and it covers the concepts that we just introduced in the slideshow. I also wanted to define acceleration. I kind of talked about it a little bit, but the physics definition is going to be acceleration is a vector quantity that is defined as the rate at which an object changes its velocity. So again, we're trying to think, okay, car is going this velocity, and now it starts to increase the velocity. Well, we can calculate how quickly it increased its velocity, and that's going to be the rate of acceleration, or how slow, right? You can gradually increase your velocity over time. And now we're going to practice. So a couple questions here, based on the slideshow, or really just one, and then looking at those patterns. Okay. And here's the next part. Because of the length of videos, and this is a little more complex, I wanted to create a video and put it in the assignment. So I've done that. Okay. So again, this is the equation. If you get a starting velocity and you have the final velocity, you divide that by time, and that can get you your acceleration. And I have a tutorial here for you. Okay, so please watch this, and it'll help you answer these questions here. And I tried to use some real life examples. Ford F-150 Raptor, the Tesla. You can see it's quite a bit faster, and it's going to accelerate faster. Okay. This one is looking at deceleration. Okay, and negative answer would be appropriate if something is slowing down. And then we're going to be looking at plotting this data. And the physics department and math department have this program called Desmos. And if you've never used it, that's okay. I've done my best to set it up for you. And I've made another video going step by step on how to use it and what to do. So please watch this video. If you watch it, it will quite literally go through the problems below. So please keep that in mind. And then use the following data points to solve for the rate of acceleration. You can click on these. So this is a little window from Desmos, and you can click on the data points. And by doing that, okay, I know the distance and I know the time. And so starting out, okay, our velocity then would be 0. And I apologize. With that, okay, we can solve for the velocity. So by knowing the distance and time, I can calculate the starting velocity, and I can calculate then the final velocity and calculate the rate of acceleration. And the example is kind of shown there, but I'll come back. I should have deleted that. And then I want you to see if you can use the equation Desmos to test your answers. So if you solved for an answer, can you open up Desmos? Again, I've plotted the data points. That's where this graph is from. Here is the quadratic equation. I have to write it this way so the program can read it. But then this slider is going to represent your acceleration. And as I slide this, I can line it up with my bullet points. And so now the question is, does this answer, maybe a little bit, does this answer match the answer that I calculated? And hopefully the answer is yes. All right. And that'll be that. So please let me know if you have any questions, and please ask for help in class. Thank you for being here, and thank you for watching this video.